Hi everybody, thank you for taking part here today for our online Space Week seminar, especially to our invited speakers, but also to all the students and educators. It's very nice to see such strong interest in exploring our understanding of the universe. This is the second CosmoVerse seminar, exploring our shared cosmic history with students and educators across Europe and neighboring areas. CosmoVerse, as you may have seen, is a network of over 400 researchers in Europe and over 600 globally, with the aim of unifying efforts in confronting the most pressing questions in our understanding of the cosmos. The main aim of CosmoVerse is to establish a synergy between theoretical data analysis and observational physicists, working on frontier challenges to our understanding of the universe, how it's expanding, evolving, and the sources of these mechanisms. So you can also follow us on Facebook and Twitter, and also on our website. Moving on to our first speaker, Professor Lavinia Heisenberg is a full professor of theoretical physics and cosmology. She has studied and been a researcher in universities in Tübingen, Salamanca, Bilbao, Madrid, Tokyo, Lisbon, and many more. She obtained her PhD from the Department of Theoretical Physics at the University of Geneva in 2014. In 2018, she won the prestigious Gustav Hertz Prize for her groundbreaking contributions to the development of gravitational theories. Professor Heisenberg's main research topics center on exploring the interplay of particle physics and cosmology and how that connects to gravitational physics. Lavinia, please start in your own time, and thank you once again. Thanks so much.
Thank you. Thank you very much for having me here. So today we will talk about the universe. So this is the Space Week. So I would like to welcome everyone to the Space Week. I am already here in space, and I would like to take you on a journey with me into space. And when we actually look at the night sky, we see all these beautiful structures like stars and even galaxies. And so they are, of course, beautiful to look at, but we can also do science with them. So when we, for example, look at these different galaxies, the first question we might ask is, what is the distance to these galaxies? Are they far away from us, or are they just the next neighbors? And using the so-called Cepheid stars, we can measure distances to many different galaxies. As you can see here in this picture, here is a star, this Cepheid star, which changes in a periodic way, so pulsates periodically, and there's a strong relationship between Cepheid's luminosity and its pulsation period. So there is even an analytical formula. Don't worry, I'm just showing it to you so that you can see that we can compute things. So once we observe the pulsation period of this Cepheid star, we can immediately obtain the absolute brightness of these stars. And by comparing this absolute brightness to the apparent brightness at our telescope, we can then directly measure the distance to these objects. And when we do that, we see that they are distributed around us, and we are happy that we have their distances, but we would like to know even more. For example, these galaxies probably don't just stand around, they have their own velocities. And one question would be then, how can we measure the velocities of these galaxies? And there we can use something that we are also very familiar with, namely using spectroscopy. So we can take the light coming from these stars and galaxies and let them pass through a prism. And this prism splits the light into this spectrum, which is very colorful, and it has these dark lines. These are absorption lines, and the physics where these absorption lines should be is determined by atomic physics. And now when we observe that these absorption lines are either shifted towards the red or towards the blue, we can deduce from that whether or not they are moving away from us or towards us. It's the same thing as when you hear an ambulance passing just next to you. When the ambulance comes towards you, you hear that the frequency goes up. And when the ambulance passed away and goes more away from you, then you see that the frequency goes down and you hear it less. So the same thing, this Doppler effect, not only happens with the sound, but also with the light. And so we use that. And what we observe is that the spectra of most of these galaxies are shifted towards the red spectrum. So this means that all these galaxies around us, they are moving away from us. So probably they heard that we have this coronavirus and they are just, running away. No, I'm kidding, but there must be some reason why all these galaxies are moving away from us. So Hubble did exactly that, what I just showed you. He took the distances using Cepheids and then plotted it against velocities using this different spectra. And then he could observe this line here. So what he could find is this low here, and he saw that the further away a galaxy is, the faster it moves away from us. So the further away a galaxy, the faster it moves away from us. And that was the first indication that the universe is expanding. So, but please don't think that we are in the center of the universe. We are human beings. We tend to think that way. You are supposed to visualize this expansion of the universe with this balloon picture, where these dots represent the individual galaxies. And now when the universe expands, the distance between these galaxies becomes larger, and the further away a galaxy is from another one, the faster they move away from each other. Okay, so using the Cepheids, we can measure quite some distances to the galaxies, roughly 100 million light years away. And if we want to look even deeper into the universe and measure even further away distances to the galaxies, we cannot use Cepheids anymore because our satellites don't have the type of precision to pin down individual Cepheids. But instead, we use the so-called supernovae. And supernovae are dying stars. Yeah, very sad, but before they die, they give rise to this big, huge explosion, and they become very bright. In fact, they become so bright that they are even brighter than the entire galaxy in which they are sitting. And we can use again their brightness in order to measure the distance to these even further away galaxies. And when we do that, we observe that the universe is not only expanding, it does it in an accelerated way. Yeah, so the Cepheids indicate an accelerated expansion of the universe. And this is something very strange. We don't really understand it. This is actually so strange that if you compare it with your everyday life and imagine you shoot a ball, your intuition would expect that this ball should go down. But imagine you observe that this ball shooted upwards and moved faster and faster away from you. And you would be very puzzled, right? And so the accelerated expansion of the universe is very similar, is very puzzling. So what is the explanation? We cannot really pin down the explanation 100%. We have some models, some ideas. We gave them even some fancy names, and we call them dark energy. So there must be in the universe some sort of an energy form that gives rise to this accelerated expansion of the universe. So it is a repulsive force. Okay, another very important information we get about the universe is actually from the very early universe epoch. So now if we accept this observation that the universe is expanding, now when we go back in time, then it must have originated from a smaller universe. So the universe was much, much smaller when you go back in the past. And because it's smaller, it becomes also hotter. Maybe you know that from your school experiments. If you have a box of gas, if you compress it, it will become hotter. So the universe at very early times was very hot and dense. And in fact, it was so hot that protons and electrons were all the time interacting with the photons, and the photons didn't have the chance to travel freely. And therefore, the universe was basically opaque and we couldn't look through it. But because of the expansion of the universe, at some point, the universe cooled down. It wasn't that hot anymore, roughly after 380,000 years later. And then neutral atom could form, and now these photons became free and they could move freely. And this is this residual thermal radiation that became free, and universe became transparent. And this residual thermal radiation, we can actually observe it, this residual heat, and this is the cosmic microwave background. These are these temperature fluctuations from the early universe. So this map has roughly 3 Kelvin, and each neighboring point has 3 Kelvin plus minus 10 to minus 5. So they differ by a very small number, 10 to minus 5. So this is really super duper tiny fluctuations. But when we look around us, especially in the sky, we see all these immense structures in the universe. So how could we get from this super duper tiny 10 to minus 5 temperature fluctuations down to these immense structures that we are observing today? And this is a big question. We again have just an idea, we give a fancy name to it, it's the dark matter. But now this dark matter is attractive and it doesn't interact with light, but nevertheless it was present in the early universe and helped that structures could form because it was giving rise to an attractive force. There's yet another puzzle when we look at this residual heat. Namely, if you take two patches very far away from each other, they were never in causal contact because the light, the photons never had enough time, the chance to communicate. Say, I have 3 Kelvin up to 10 to minus 5, please adjust also your temperature. So how can causally disconnected regions have the same fluctuations? And also there we have just an idea, and we believe that there must be an inflationary phase, yet again an early phase of accelerated expansion, and actually these two patches were in causal contact in the past. So we have this dark triangle, dark matter, dark energy, and the inflaton in order to describe the observations in the universe. But we don't know what is the origin of this dark matter and what causes these two accelerated expansion phases of the universe. So we seem to have an accelerated expansion at very early universe and a late time accelerated expansion in the late universe given in this dark energy phase. And is dark energy just a constant, or is it something dynamical evolving in time like the inflaton? So these are fundamental questions in cosmology. Now, these were all observations, but how do we reconcile all this in a theory? We have to look at our theory of gravity, namely general relativity. And there Einstein plays a fundamental role because thanks to him, since 1915, we have the theory of gravity. And he went and postulated that gravity is property of space-time and that gravity is geometry. And this was a quite radical change of view because until that point, we had only Newtonian's gravity. And Newton postulated that gravity is a force and its effect is instantaneously. So if you have two objects like Earth and Moon, the gravitational force between them propagates instantaneously, and the force is inversely proportional to the distance squared. But Einstein said, no, there is a maximum speed. You cannot propagate things instantaneously. Nothing can propagate faster than light. And gravity is not a force. It is the geometric property of space-time. So what Einstein did was he took the three-dimensional space, the x, y, and z, and then combined it with time. Then he had his space-time, and he claimed that now this geometrical property of that space-time describes gravity. So this is quite mathematical and abstract. So in Einstein's perspective, imagine you have a complete flat space-time, and now you put something like Earth on it, something which has mass. It will curve this space-time. Maybe you have a second object like the moon, and now all the particles, all the trajectories, all the fields living in this space-time will follow the trajectories given by the curvature of this space-time. So you might be familiar with this when you jump on a trampoline, and the trampoline represents exactly this type of curvature of space-time. So Einstein thought that gravity and general relativity equals to this curvature of space-time. And is this geometrical description unique? In fact, no. There is a trinity, as I will just illustrate in a second. So in this trinity of gravity, we have shown that, of course, you have the first interpretation formulation of gravity a la Einstein, based on curvature, but there's actually a second completely equivalent interpretation of gravity, but this time based on torsion. And the third equivalent formulation of gravity is then based on non-metricity. So these three are geometrical objects that we can use about the space-time in order to describe gravity. So these are really purely mathematical objects and approaches. If you cannot understand those, don't worry. These are really supposed to be quite mathematical and abstract way of thinking about gravity. But maybe I can try to help you to visualize it nevertheless. So imagine you have a vector. So vector is something which is pointing in a given direction. And now if you have curvature and you have this vector here pointing in a given direction, and you move it along a closed path and you come back to where you started, if this direction has changed, then you know that your space-time has a non-vanishing curvature. Yeah. So if you have this vector here and it moves along this path and comes back to where it started, and you see the direction has changed, this is an indication, okay, you have curvature. And now what happens with torsion? Imagine you have now two vectors pointing in a given direction, and you move them along each other. And if this parallelogram doesn't close, then you know that your spacetime has a non-vanishing torsion. When you parallel transport these two vectors along each other, if this parallelogram doesn't close, you know your spacetime has torsion. How about non-metricity? Now, if you have a vector given with a length, and now if you move this vector along given a path, and if its length changes, then you know your spacetime has a non-vanishing non-metricity. Okay, so changes of lengths indicate non-metricity. So we can actually then postulate the coincident general relativity if we then say gravity is non-metric. So due to this non-metricity property of the space-time, and it's due to changes in length. So these were all geometrical abstract way of thinking of gravity. There's also, let's say, a naive visualization that we could try to do in the same way as we did with the trampoline. So imagine we start again with this flat space-time. Now I put an object on it, like Earth. As you can see, the space-time remains flat. There's no curvature, even if I put another object. Nevertheless, the trajectories of the particles and fields, they are exactly the same thing, but it's now not due to curvature, but rather due to the fact that the lengths of these particles associated to these particles change. So as you see, it's just a different perspective, different interpretation of the same thing. Okay, now let us play a Gedanken experiment, and let us imagine a universe in which Einstein had never existed. I know this would be really very sad, but this is just for a minute to do our Gedanken experiment, in which let us imagine a modern version of Einstein. And this modern version of Einstein, which Google suggests would look like this, doesn't care about geometry and about this abstract mathematical thinking of space-time in terms of curvature, non-metricity, but rather wants to try to describe gravity in terms of a particle, like we do in particle physics. So this modern version could be actually also a woman, not necessarily just a man. Doesn't matter. So she or he would have learned all the standard techniques of particle physics. And so she or he would have tried to describe gravity by means of a particle. So in the same way as when we try to describe the electromagnetic interactions, where we say they are exchanging this photon particle, where we say that these two electrons, they know about each other because they are exchanging all the time this photon particle. We can say the same thing about gravitational interaction, and we can say that the Earth and the Moon know about each other because they are exchanging this graviton particle. Yeah, it's again a completely different perspective. Now we say that the Earth and the Moon are exchanging this graviton particle, and that's the reason why they have the gravitational interaction. But if we accept this particle physics perspective of gravity, what is the most natural candidate for the graviton particle? And we can answer that by just watching the next video, and it will summarize all the knowledge we have about gravity. Gravity is attractive.
Each end of the bar, we put a lead ball. Two balls balance, and the bar is free to turn. Now we put another ball on the left side of each of the two original ones. If everything attracts everything else, the balls should attract each other and the bar should move.
So gravity is attractive, as you can see.
There is an attraction of gravity between the lead balls.
10,
Gravity is democratic.
7, 6, 5, 4. Counters on, 2, 1, release.
Gravity interacts with light.
Even light can escape the effects of gravity. As crazy as this sounds, proof conveniently arrived in 1919 in the form of an astronomically large experiment based on a solar eclipse.
General relativity said that if you look at a star on a path of light that goes right past the sun, you would see it shift just a little bit because of the gravity of the sun. So Arthur Eddington actually went out to test that theory during the solar eclipse of 1919, and actually photographed stars when the sun was blocked by the moon. You could see the stars behind it.
The ability to see objects that were actually behind the sun proved that objects could warp space-time.
Gravity is long range. Okay, so let us summarize what this video told us. So gravity is long range. So whatever particle this graviton particle is, it has to be massless. It exists as a classical theory, so it cannot be a fermionic particle. It has to be a bosonic particle. And it is attractive, so it cannot be like the light, like the photon particle. And it interacts with light, so it cannot be like the Higgs boson. It has to be something else. And it turns out that the graviton has to be a massless spin 2, a tensor particle, and then when you sum the interactions of this particle, you get really general relativity. This is just to show you that we can also describe gravity in terms of particle. Now we have Einstein's field equations. I think you have to see that once in your lifetime at least. So this is the basically the metric dynamics on the left-hand side, what gravity does, and on the right-hand side you have all the matter fields around us. And then we have to introduce these ingredients, dark matter, dark energy, and the inflaton field. And also we are assuming the cosmological principle, which states that the universe on large scales is more or less homogeneous and isotropic. Despite the many successes that we have in cosmology, there is also quite some crisis. So first of all, we don't really know how to get the start of the universe from pure quantum fluctuations and then go into this inflationary phase. There is this dark matter and dark energy, which makes 95% of the total budget. And we don't have really the candidate of quantum gravity, where we could combine gravity with the quantum mechanics. And we have singularities popping up, like the cosmological singularity as well as the black hole singularity. And there seem to be also some observational tensions, like the H0 tension. Okay, so therefore we try then to consider options where we move away from general relativity, and we have to do extensions, and these extensions could be either classical or quantum. So we need your help. I hope you got motivated that gravity and cosmology is really a cool subject to study, and so please do study physics at the university and help us with all this crisis in cosmology. All right, thank you very much. I stop here and I'm looking forward to our discussion later.
So thank you very much, Lavinia. Very interesting, insightful presentation.